Welcome to Slingshots with Quadratics. This will be a short video that analyzes a task using different forms of quadratic functions. We have discussed three forms of quadratic functions in class, but in this task we are going to go more in depth with how we use them. As a part of a new attraction at a water park, we are in charge of installing a slingshot that shoots off the side of a cliff so that the riders are propelled into a small lake. To add thrill to the experience, we want to add some dangerous looking rocks at the bottom so that it looks like our riders might hit them, but we as mathematicians know they are perfectly safe. Let's take a look at the path the riders might take. Look at the shape of the rider's path. This curve follows a well-known type of curve that physicists study, and we have been studying this curve recently in our math class. It's called a parabola. We have also learned about what kind of functions are used to model parabolic situations, quadratic functions. We have been talking about quadratic functions in class for a few days now, and we have learned several different properties about quadratic functions. Let's review some of them before we get started. We know there's an x squared term in our equation. The graph of a quadratic makes a parabola shape. The lowest or highest point of a parabola is called the vertex, and that parabolas have a line of symmetry that run through the vertex vertically. Let's revisit our work site to make some measurements. We know that from the lake level to the top of the cliff is 12 feet. When we read the Slingshot Machine Owner's Manual, it tells us that the average person rises 4 feet in height and advances 2 feet horizontally at the highest point of flight. Excellent. So now we can move 2 feet horizontally from our starting point and 4 feet vertically to find the tallest point our rider will reach. When we finish out the shape of our projectile motion, we see that the point we just plotted is the vertex of our parabola. During class, we have seen quadratics in three different forms: standard, vertex, and factored. Let's take a moment to review how each one looks. Standard form places the variable terms in decreasing degree, second power, first power, and then the constant, where a, b, and c are coefficient numbers we can change around. We know how to take standard form and factor into two binomials also, but most recently we have reviewed vertex form, which uses the coordinate of the parabola's vertex, hk, to construct the quadratic equation. Now that we remember which equivalent forms we have to work with, we need to decide which is best for our first goal: to find an equation that represents the path of the projectile person. Standard, vertex, and factored form are all equivalent representations of the same function, but we have these different forms to utilize our information more easily. Let's consider what we know about our problem. We know the starting point for when the horizontal distance is 0 and the height is 12. And we know the vertex of our parabola, where we've gained 4 feet in elevation and 2 feet horizontally. With these two pieces of information, it looks like the vertex form will be the most straightforward way to translate this into a quadratic function. This might be easier to work with on a coordinate plane. Then we can apply this to our slingshot attraction later. On our coordinate plane, we've graphed the starting point at 0, 12 and the vertex at 2, 16. From the picture we drew on the water park, we know a concave down parabola, or a parabola that opens down, will pass through these 2 points. But we need to find the exact equation that produces our representation. Let's start with our basic vertex form and see what we can substitute. When we replace hk with 2, 16, the vertex point, we have our next step. Now we have xy and a unknown. Since a is a parameter, we are trying to search for its value. We do know a point xy on the graph, so let's take the starting point 0, 12 and substitute for xy. Now we can use algebra to solve for a. Subtract 16 on both sides, divide by 4, and then we find that a is equal to -1. We have all our missing pieces. To write the final quadratic equation, we can plug in our h, k, and a values into the original vertex form like this. Remember that x is representing our horizontal distance and y is representing the vertical distance. Using this equation, we can graph our parabola and it should model our rider's path while passing through the starting point and hitting a maximum at the vertex. Let's use our graphing tool to check. Perfect, our graph does just that. For the next step, we need to use our imagination a little bit. What if we came across a similar situation but did not know the starting point where the horizontal distance is 0? In this case, the y-intercept. We would be able to find the equation based on knowing the vertex and vertex form, but it isn't obvious what our y-intercept would be. Which form of quadratic functions makes the y-intercept obvious? Standard form. Why? Because the parameter c is the y-intercept of the function. Perfect. You might be wondering, well, since standard form and vertex form are equivalent, there has to be a way to convert what we already have into standard form, right? And you would be right. So on our journey for the value of c, let's start with our vertex form quadratic function that we found earlier. Let's do some algebra. Rewrite the x minus 2 squared as x minus 2 times x minus 2. Now we use distributive property to FOIL it out. We still have a negative we need to distribute. Now we can combine like terms. It looks like we are left with standard form, where a is equal to -1, just like it did for vertex form, b equals 4, and c is equal to 12. Great! So we found our c value. Does what we found make sense? Well, from our standard form equation, 0, 12 should be the y-intercept, and when we look at the graph, that is exactly what we find. And 12 feet is how high the cliff was. As a side note, I've graphed both the vertex and standard form together, and as you see, they overlay one another, another proof that they are equivalent. So far, we have found standard and vertex form, but we are still missing a crucial piece of information. Remember that our end goal is to find out how many feet of rock we can install at the bottom of the cliff to add to the thrill of the slingshot attraction. Well, that means we need to know this distance. How does that translate to our coordinate plane? It would be this distance, or the value of x where the graph crosses the x-axis. To describe this point in context, it is when the rider hits the water. So, we need an easy way to determine what value x has when y is 0. Looking at vertex in standard form, if I substitute 0 for y, I get some nasty equations with squared and non-squared x's. That doesn't sound easy to me. Again, I could ask myself, well, since factored form is equivalent to both standard and vertex form, can I not just convert my existing equations into factored form? Of course you can. We have been factoring standard form quadratics for a while, so let's take this equation and see if we can factor. The first thing I would do is factor out a -1 so that our leading coefficient is positive. It makes our factoring algorithm or procedure work. There are several methods for doing this, but I will perform my favorite here. List the factors of 12. Now ask yourself, what two factors multiplied to give me -12, but add to give me -4? Since my product is negative, I know one of my factors is negative, and the other is positive. This helps me narrow it down to -6 and 2, as shown. Now I can take those two factors and make them into two multiplied binomials. If you want to check your work, you can FOIL this result to verify you arrive at the standard form you started with. And there you go, factored form. Don't forget the negative. We have found an equivalent equation, but we are searching for the x value when y is equal to 0. This is much easier with factored form. And to see y, let's substitute 0 for y. Let's divide both sides by that -1. Now we have two binomials multiplied together to produce 0. By the zero product property, at least one of them must be 0, so we can evaluate them separately. By adding 6 to the first and subtracting 2 from the second, we find two solutions, x equals 6 and x equals -2. So which is our answer, 6 or -2? If we think about our context, it doesn't make any sense for the slingshot to shoot someone backwards 2 feet, and this isn't even towards the lake, so we can eliminate that result. The parabola crosses the x-axis at -2, but in the real world our slingshot riders do not. Instead, they impact the water 6 feet from the base of the cliff. Therefore, as the designers of the attraction, we have 6 feet of space to work with for installing rocks, although we might want to leave a little extra space just in case. Great! Let's review what we have found most useful out of each form of a quadratic function. Vertex form is great for just that, the vertex. We can easily locate the vertex, and therefore the axis of symmetry. Standard form was great for the y-intercept. The c value hangs out on the end, untouched by other operations, so it is easy to use. Additionally, we can look at the a value to see how sharp our curve is going to be. Remember that this is the same a value that was present in vertex form. And factored form was great for finding the roots of the equation. We found where the graph crosses the x-axis, and as we saw in our problem, the roots are meaningful in lots of different contexts. All of these forms are suited for different types of information, but at the end of the day, they are equivalent forms of the same quadratic function, representing the same information.